Okay, let's move into the worksheet number 5 from the lecture number 5. So lecture number 5, we basically talk about the rotational motions for you to get an understanding about real life problems that we discussed earlier. We never think about the rotation of the object. Simple example that you can see is if you have a ball, if you kick this ball, what will happen to this ball is going to kick it, right? So when you kick the ball, what will happen to this ball? We'll say it's going this way, right? So, but this ball actually not like sliding on the ground. What will happen is this ball keep doing rotation and keep doing rotation, and then it will come to the rest because of the friction sometime later, right? So now because of this rotation, what will happen to the object is it keep changing this angle of the motion, right? In addition to this, object is moving some distance in your horizontal ground, right? So now there are two things happening. One thing is change in x. Other thing is change in the angle of the rotation that you can see it in here, right? So now we need to include this rotation part into the parts that we discussed on 4 chapters earlier. But we are not going to do that big complex calculation for your class, but we need to understand when there is a rotation, then you need to consider the rotational motion. That means you need to include rotational quantities. Right? So that means simple example is theta angle is important in this case, right? So that means displacement of rotational motion, we call it as the rotational displacement that is measured by using angle theta, but in radians. So you need radians. Okay, unit of radians. So now, after you know that you have angular displacement, definitely we have angular speed and we have angular acceleration, angular force, angular momentum. Everything that we discussed earlier, we need to add the prefix angular or rotation to that quantities. According to the displacement definition, we will be able to define the other important physical quantities. But what's important thing that we discuss is how this angular speed and the translational speed going to relate to each other. As a simple example is conceptual kind of understanding. What that means is if you ride the merry-go-round, as I discussed in the lecture part, we'll say there is a merry-go-round and you and your friend is going to ride the merry-go-round, but you like to sit in two different places, right? When this happens, when the motor start the rotate the merry-go-round, what will happen is this merry-go-round is keep rotating. That means you and your friend rotating with the same speed. That is, we call it as the angular speed. Angular speed is the speed of this merry-go-round. So we use the letter angular speed and we use the letter omega for that. Omega is measured by using radians per second. Okay, radians per second is the omega. This is not negative sign. That's my line that I had in bracket. Okay, radians per second. Now it is basically displacement divided by time, as we know how rate of change of this angle is the basically omega is, to get an understand it, right? But what is important thing is you and your friend both has the you and friend both has same omega. That's the important thing. right? That means angular speed does not change when you and your friend ride the merry-go-round. It doesn't matter how many people on the merry-go-round, they all has the same omega, right? But important thing is you and your friend has different different translational speed. That means this u has ry distance to the center. This is the center. And your friend has the distance, this whole distance. This is your friend, will say our friend, right? Now, definitely you and your friend has the different radius. Because of that, what will happen is your friend feel faster, F feel faster, because V for friend is greater than V for you. V is linear speed, not the angular speed, linear speed. Why? Because your friend is going on this circle, but you going on this circle because you have a smaller radius, right? So now this velocity that we are talking in linear speed is related to the radius and the omega. You see that when the omega is a constant, then R and V are linear relation. Yeah, that's the important thing. When the R is greater, more moving faster. When R is smaller, moving slower. That's one of the most important part that I discuss in the rotational chapter for you, because it's very important that you understand that. And in addition to that, definitely we discuss about the rotational pause. So rotational pause, in simple way that we discuss the pause, is just a pause by using the F. But when you come to the rotational motion, we are not able to talk about the just the pause. We need to talk about the pause time distance. That is, we call it as rotational pause. We call it as the torque and use the symbol tau for that. And tau is equal to R times F times sine of theta. It's very important. What that means is, if this is your rotational axis, or we'll say pivot point, then if I apply the pause in this place as F, and if distance is R, if this angle is theta, then we call it as tau equal R and F and sine of theta. But in most of the problem in your class, we are doing this theta angle is 90 degrees. When theta 90, everybody know sine 90 will be just 1. Because of that, in your class, tau will be mostly calculated by using R and F. But make sure your R and, I'm going to say, when R and F are perpendicular mathematical symbol, perpendicular to each other. Most of the problem, I would say almost all questions in your class we are doing, they are perpendicular to each other because it's easy to calculate, right? Now units of this one will be R measured by meters, F measured by Newton, so units will be Newton meters. That is another quantity that we discussed. In addition to that, we discuss about the moment of inertia, right? So moment of inertia is another quantity. I'm going to use this space for that. Okay. So we discuss about the moment of inertia. So make sure that you watch the lecture before you watch this one, moment of inertia. Okay. So moment of inertia, we use the symbol I. I basically calculated how mass distributed of the object, right? Simple example, if you have a solid ball, if we have a same size hollow ball, so if you calculate the moment of inertia for these two objects, I2 will be greater than I1, because hollow sphere, you have the masses all the way outside from the center. You're going to rotate on this center, right? But this one you have masses everywhere because of that hollow sphere has more moment of inertia. When you have more moment of inertia, that will basically slow down the motion. More moment of inertia, slow down the object. That means it has more friction. That means I'm going to say this one has more friction. In simple word, more friction. Okay, so I think I covered all the materials that we discussed. And also one last thing we discussed is actually angular, write it here, angular momentum. So similar to the momentum that we discussed earlier, linear momentum, we discussed the angular momentum. Angular momentum, we use the symbol L for that. And it is equal to I, that means moment of inertia times the angular speed. So it's very important. This is also a conserved quantity. That means usually in the system, when you write the conservation of that, that means when the I is greater, omega is smaller, omega is greater, I is smaller. That's what this formula to show to you, right? These two are exchanging by up and down, or one is larger, other one is small. I think I cover most of the material that I talked in lecture 5. Actually, it's a summary of the lecture 5 for you. Okay, so now let's directly move into our questions. Okay, so now my first question is, you sit on the outer rim, the merry-go-round. It's the same example that I did earlier. You're going to sit the outer rim somewhere here. This is you. And then it's very important that you read the question very carefully, outer rim of the merry-go-round, and your friend is sit midway. So I can give you, your friend is sit 1/3 of way. I can give you, your friend is sit in the middle, right? According to that, you need to answer your question correctly, right? Since it is saying halfway, definitely what we know is we can write this distance for your friend, and you has 2r distance, okay, because it says midway, right? And then merry-go-round make one complete revolution every 2 seconds. So as soon as you understand that, you need to understand what is given. Make one complete revolution every 2 seconds. That means to this person to come back to exactly same position take 2 seconds. That is, we call it as the period. So this given period equal 2 seconds. Okay. And what can you say about their angular speed and linear speed? In first, it's asking what can you say, next asking calculate and discuss, right? So now you should be familiar with the symbols, right? So angular speed, we use the omega. Linear speed, we use the velocity, right? So now you going to write y, and friend both has the same omega as we discussed earlier, right? Because merry-go-round is rotating with the same angular speed. And then u has greater linear speed than your friend. Why is that? Because you are sitting on the rim, your friend is sitting in a distance less than the u, right? Because of that. Now we ask to calculate and discuss. We already discussed this. Let's calculate it. How do we calculate it? So now to calculate v, so we know that we calculate by using r times omega. So now don't know that I can definitely calculate this one, but I can get the relation, right? V equal r times omega, right? So now what will be the omega is, you need to understand the period is given here, right? That means frequency equal 1 over period, 1 over 2 seconds. right? So now if you need to find the angular frequency or angular speed, that will be 2 phi and the frequency. So that will give you 2 phi over frequency 2, and that will give me, let me say 2 seconds, yes, that will give us the omega as phi, right? So now if I want to calculate this one for you, let's calculate it for you. Since the R is not given, I cannot directly calculate what it is because we need the R value, but I'm going to keep it in terms of R in here. Okay, so V for the U will be, you see that the distance is 2R now, 2R times phi. And because omega is phi in here, right? So for your friend, R is just R and phi. Okay, I will keep as it is since the R is not given. I just want you to compare this, and what you can say is you rotate twice faster than your friend. That's the final answer, that final conclusion that we can get it in here. Twice, you see that it is twice of this one. Okay. Okay, so now, yeah, let's move into the question number 2. So now how do you, how do you relate RPM to angular speed? So that's the first question. So RPM is what? RPM means rotation per minute. That's what it means, right? How do you relate to the angular speed? Actually, this is angular speed in different units. Angular speed is the same as the angular speed, but not in standard units, SI units, not in SI units. So angular speed, we know that it is in SI units, it will be radians per second, right? What is given is rotation per minute. Okay, so that's the only difference. You need to convert minutes into seconds accordingly. Okay, so what will be the units of the angular speed? Done already. If the propeller of the airplane is rotating at, so you always check the units when you do the problem. So this is given. So now we have omega is given as 10 pi radians per second. Okay, how many revolutions per second is that? Okay, so see that what it's asking, how many revolutions per second is that? So in other words, what is asking here is actually frequency. How many revolutions per second is the frequency, right? So now how do you find the frequency? You remember that the omega equal actually 2 pi and the frequency, because the reason is when you make a one complete revolution, this angle that you are changing from here to here is 2 pi radians. Because of that, you can get this relation and then you can find the frequency. So I'm going to answer this question. Okay, so frequency is the question, what the question is asking. Now frequency equal omega over 2 phi. That means 10 pi divided by 2 phi, and then you see that it is just 5 per second. Okay, units is hertz. Okay, so now calculate the frequency. I already done that. Calculate the frequency means exactly same quantity. These two are asking same quantity, two different ways. And calculate the period. So period is equal 1 over frequency. So that means 1/5. That means it is 0.2 seconds. Okay, so now let's move into the next question. What is the linear speed of a child seated 1.2 meters from the center of a steady merry-go-round that makes one complete revolution in 4 seconds? So read it very carefully. Your question in the exam, so the quizzes may be a little different than this. Okay, period is 0.2 and radius of the person that's sitting on the merry-go-round is 1.2 meters. Okay, so now question is asking what is the linear speed? So what we know, we can calculate the linear speed if I know R and omega. So R is definitely known, but what is the omega is? Now I need to relate this period into the omega. How do you do that? So you calculate the frequency first. Frequency will be 1/period. That will be 1/4. I'm just going to keep as it is. And then omega is what? Omega is 2 pi. That means 1 complete revolutions times the frequency. That will be 2 pi and 1/4. This will be equal to pi/2 radians per second. That's the angular frequency or angular speed, right? After you calculate that, you will go here and plug it. So I need the linear speed equal R times, I'm going to actually use the values in here because we already have those values. Put it in here. R equal 1.2 meters. This value is R. And omega, I already find 5/2 times 5/2 and units meters per second for the linear speed. Okay, so now let's plug this into the calculator and I hope my answer is correct. I have V equal 1.9 meters per second. Okay, now let's move into the question number 4. So question number 4, there is a girl and a boy riding the seesaw. This is related to rotational force or the torque. If the girl's mass is 50 kilogram and the boy's mass is 25 kilogram, and let's draw a diagram. So you have seesaw and your 50 kilogram, going to write it as the mass of the girl and this is mass of the boy, right? So mass of the girl is 50 kilograms sitting. Girl is sitting 2 meters. So say girl is sitting here and mass of the girl and sitting this distance, I'm going to say this distance, always use the symbols, that's the easiest way. This I'm going to say RG. RG is distance from this pivot point to here, RG. Okay, RG and MG is given, but there is a boy sitting here and mass of boy, there is no distance known yet, but we're going to find this distance as our boy, right? So let's write down what we know first. Mass of the girl, we know 50 kilograms. And then we know the distance to the pivot point for the girl, 2 meters. And mass of the boy, we already know 25 kilograms. And RB is the one we need to find it out. Okay, so now when you have a seesaw balance, that means this girl or boy not moving up and down. They are going to stay horizontal. That's we call it as equilibrium, right? That's what the equilibrium means. So when it is at equilibrium, we know that rotation coming from boy, or I would say first counterclockwise rotation equal clockwise rotation. That means it is balanced. Whatever rotation doing by the girl should be equal to the whatever rotation doing by the boy in this point. That is, we call it as pivot. Right? So now which one do the counterclockwise and clockwise is you need to decide by watching your diagram. So now this girl is pushing seesaw downward. What that means is if boy is not there, this seesaw going to be rotate this direction. That's the direction of the force, right? That is, we call it as clockwise. After you realize that it is clockwise from the girl, I'm going to write tau from the girl, right? And now what the boy do, boy sit on the other side, force of gravity of the boy pushing this way. So now you see that this is going to whichever circle that has doing the rotation, this direction, that is important to understand these directions, okay? It is counterclockwise. Tau from the boy is counterclockwise. Clockwise coming from because of the clock direction. Counterclockwise means it's doing the opposite rotation. Okay, after you realize that, then we can write the tau formula. How do you write the tau? Tau in general formula is R and F when R and F are perpendicular to each other, right? So now let's start from the girl. Girl have F this way. So we start with the boy. So let's start with the boy. Boy has the force this way. This force is the force of gravity that will be mass of the boy times the G, right? So let's write it. We have a distance RB, just writing this formula, and then your force of gravity is the force we have, mass of the boy times the G. We do the exactly same thing for the girl. Force of gravity for the girl will be mass of the girl times the G, and that will be distance R girl and girl times G. So now divide by G both sides, right? What is question asking? RB. Then solve it for RB first. RB equal, I'm going to divide by MB both sides. Then I have MG divide by MB and the RG. So now I'm going to plug it. MG over MB. MG is 50. And MB is 25. And RG is 2. Okay, so always multiplication, write it as the multiplication, otherwise it's display as a decimal place. So we know that this is twice of that, then RB will be equal to 2 times 2 is 4 meters. Okay, so that's it. So you don't want this all the information as I try to explain everything, but what is happening is this girl doing the rotation counterclockwise and clockwise, and boy doing the counterclockwise, and then RG times IMG should be equal to the RB times MB. Then you can find the distance. You can see that 2 times 50. 2 times 50 equal 25 times 4, right? That's why you get the 4 as the answer. Okay, so now let's move into the number 5. In which of the cases shown below is a conceptual question that I want you to understand the formula R equal tau equal R times F. Important thing is this you can write only when you take R and F are perpendicular to each other. If they are not perpendicular, you need to find the way to make them perpendicular to each other. Okay, that's the observation in here. Now let's start. 1, 2, 3, 4. All has exactly same force. It is given. Okay. Case one below is the torque provided by the applied force above the rotation, and all four cases magnitude of the applied force is the same. That means this all has the same force. Now let's move one by one. Number one is the first one. So I have the force here, right? Force here. And I need the pivot point. This is where the pivot point is. I need to find the distance to that. Okay, since F is same, we're going to work with the distance first. Now, perpendicular to this one, you need to extend this one and find the perpendicular distance. This is the perpendicular distance. I'm going to say R1. Then R1 times the F will be the torque from the first one. Okay, so tau 1 equal R1 times the force. That is for the first one. And now let's move into the second one. In the second one, you see here, this is the force, right? So now it's really important that if you extend this line, that will go through the pivot point. What that means is they are not perpendicular in this case. They are parallel to each other. Then sign of 0 is the answer that you are coming in here. Because of that, there is no R2 distance. Because of that, tau 2 actually equal 0. Yeah. And now let's move into the third one. So third one, force is here. I need the distance, perpendicular distance to that. I'm going to make a line. These two are now perpendicular. Now this is your R3. Now tau 3 equal R3 times F. Okay. Now last one I have another color green. Okay, so this is my force, right? And now distance to that one actually I already drawn. R4 and R1 are equal actually. Tau 4 equal R4 times F. Since R4 and R1 equal, I can write R1 times F. Now, by watching those things, what we know is R3 is greater R1 equal R4 and R2 is actually 0. Equal to 0 if you want. Right? So now, because of that, what you can see it in here, which one is greatest? If is the same, then this will be the greatest. Because of that, tau 3 is greatest, but tau 4 and tau 1 are the same. Least will be tau 2, that also equal to 0. Okay, always for the ranking, make sure that you use the which one is greater, which one is smaller, which one is equal, because you know that those symbols, right? This is we use it for greater on left side. If the left side is greater, we use this symbol. If the left side is smaller, we use this symbol. If they are equal, we use this symbol. Okay, so those are the three symbols that you need to use for the ranking. Okay, now let's move into the number 6. Okay, number 6 actually asking you to calculate the torque by lifting the child. So you're going to lift the child of 20 kilogram by using your finger, your hand, but you're going to use your soldier joint without bending the elbow, right? What that means is the person try to lift the child, has long arms, but by just stretching the arm, not going to bend the elbow, right? So now this child has the force as given force of gravity. So that force of gravity of the child, you know that the mass times g, distance to this one is r. So now we know that tau equal, they are perpendicular, r times fg. You can write it as first formula, and then you can write the next formula, r times f, and this case r times m and g. Okay, so now this is r and this is m. Okay, you're going to plug it. Make sure that all are in SI units before you plug it. R and mass is 20 and g is 9.80, and then tau you're going to calculate by using these numbers. Units is newtons and meters. Okay, so what I have is 156.8. Okay, let's go into the next question. So there are three objects. From the rest, you're going to roll on the ramp. There is a ramp like this, right? It's very hard to draw it in my view. And there are three objects. One is the solid sphere. And then you have hollow sphere. And then you have solid cylinder. Okay. Three things there. You're going to start to roll them down. So you're going to let it go. When you let it go, these objects going to be rolled on the incline, come to the bottom of the track, right? But what is important thing is happening, each of the object has the same radius. We'll say we're going to use the R symbol for that, and same mass, use same. Which object will have the greatest moment of inertia? That's the first question is, right? So you remember that you have the table given in your lecture note, and the moment of inertia formulas will be given for the solid sphere. I'm going to write it in here, solid sphere. Solid sphere, I'm going to use the solid sphere. I have I1. I1 is for the solid sphere is given as 2/5 m and r square. And next one is hollow sphere. We know that hollow sphere should have a greater moment of inertia than the solid sphere. That's also I pick from the table 2/3 m r square. So next one is solid cylinder. So solid cylinder, I'm going to label it as I3 has half m r square. Since mr square is the same, the coefficient is the one it matters to you. 2/5 is 0.4, 2/3 is, you know that it is 0.6667, you can say, and 1/2 is 0.5, right? That means by watching these coefficients, you can see which one is greatest. Greatest is I2. I2 is greatest. Next one will be I3, and next one will be I1. Okay, so now moment of inertia is greatest is, you can write the answer to the question, which object have the greatest moment of inertia? That means I2, hollow sphere. Greatest, I'm going to write I since I don't have a space. That's the first question. And now second question is asking which object landed on the ground. You remember that whichever has more moment of inertia will have a lot of friction. That means it's slowing down. That means the ground is, first one reach the ground is lowest moment of inertia. That means the object has lowest moment of inertia. That is the solid sphere is the one come to the ground first. So solid sphere land the ground first. Why? Because it has lowest moment of inertia. Okay, so now let's move into the number 8. And number 8 is asking, you have pulling the weights inward on the rotational inertia of the person reduce the half its value by what factor its angular velocity change. So now you see that the weight inward rotational inertia of the person reduced to the half its value. Whatever he had the first is going to reduce into half. Okay. So now this is actually conservation of angular momentum. Conservation of angular momentum. Conservation of angular momentum. Right, to remember that the L that I talk in, that means whichever start Li should be I and F are for the final. This is I initial. This is your I final basically, right? And so now L initial, we know that we can write I initial omega initial equal I final omega final. That's the moment of inertia concept. So now when I final is go to I over 2, what will happen to the omega final? That's the question is, right? So this one going to be I initial over 2. Right, when it move into the half of the initial value, that means it's actually lower down, right? That means omega final definitely should be increased because you decrease in the moment of inertia. But how much you need to increase the omega final is, you can definitely see it from here. You need to double the omega final to make it initial. So this one I need to change into twice of omega initial. Then you see that this 2 and this 2 cancel out. Then your left side and right side are equal, right? So you can think in different way, but that's the things you happening, because left should be equal to the right. If I reduce I final into half, then omega final I need to increase into twice. Okay, to make it a constant. So omega should increase by twice. Okay, so now let's move into the next question. Okay, so next question is talking about the center of mass of the object. Next two questions actually. Center of the system of object. So in this case, you have two objects separated at 10 centimeters. Always draw the diagram. You have 1 kilogram object, and then you have 0.5 kilogram object, and they are sitting 10 centimeter different. That means if this one sitting at 0 centimeter distance, this is sitting at 10 centimeter distance. Okay, so now this one I'm going to write M1 equal 1 kilogram, and this is I'm going to write M2 equal 0.5 kilogram. Okay, and so now find the center of mass point. So now everybody understand that center of mass formula, that is the center of the system. It is closer to the heavier side always, right? That means I definitely know the system center of mass will be located closer to the greater mass object, closer to the M1 in this case, right? I don't know that distance, but I'm going to write it as X center of mass is equal, use the formula given in your lecture, M1 times distance, M1 times distance to that one, I'm going to write R1 first, and M2 times distance to that one, R2, and divide by this general formula. If I have two masses, if I have three masses, I definitely need to add it, right? Okay, so now M1 times R1. So now distance that I label here is the 0. I'm going to find the center of mass from this point, because in the question, in the first part, asking center of mass from the left object. This is what the X center of mass that I'm going to find it out, XCM. Okay, so now from that point, R1 to M1 will be definitely 0. I hope you guys understand that. M1 is 1 kilogram. Let's plug it. 1 kilogram. Okay. And distance to that is 0. And plus M2 is 0.5 kilogram. Distance to that is 10 centimeters. I'm not going to convert into SI unit here because I'm just calculating the distance. If you use the same units for the distances, then I'm going to get the same units at the end. And this will be adding the masses plus 0.5. right? So now this answer, everybody can see this part is basically 0. Because of that, you have 0.5 divide by 1.5. So units centimeters, that means x cent of mass from the left object, as the first question asking, will be 0.5 divided by 1.5. 0.5 divided by 1.5 is 3.3. I'm going to keep 3.3 centimeters. Now my next part of the question is actually asking, because in your exam questions, I may ask it from the left object or I may ask it from the right object. Now next part is asking from the right object. What is the distance to the center of mass from the right object? That definitely you can see. That means if I find the center of mass here, that means I need this distance. Right? How much is that? You don't want to recalculate it after you find it from the left object, or you can recalculate it if you want. But x center of mass, this is from the left object. Right? From the right object, x center of mass will be 10 minus, because you need to subtract the 10 minus the 3.3, right? So 10 minus 3.3 will be, how much is that? That's very simple calculation. I have around 6.7, right? 6.7 centimeters. This answer is from right object. Okay, next question is very simple. Where is the center of mass point located on symmetrical donut? It's very hard to find the symmetrical donut in the donut shop, but we'll say I have symmetrical donut. Now donut material will be here, right? But the center of this donut will be where? I just want you to understand that some objects, there are center of mass which outside from the object, especially center of mass of this object is sitting at the center of the donut. Center of the donut, right? Although there is no donut material inside here, but center of the donut will be the center of mass of that object. Okay, I think this is my last question. Okay, include little calculation to get understanding about the kinetic energy. So we discussed about the kinetic energy earlier. You remember that the kinetic energy for translational motion, if I have a mass moving with velocity, that will be the kinetic energy. But when you come to the rotational motion, I have rotational kinetic energy. I'm going to use rotational kinetic energy, RKE, or you can say kinetic energy rotation, right? So rotational kinetic energy equal half I and angular velocity squared, I omega squared. Okay, that's the rotational kinetic energy. So now, when you have rotational kinetic energy, I'm going to match with what I had on the lecture. I use the rotational kinetic energy to replace this translational kinetic energy in this is just a notation. Okay, okay, but now let's read the question. Two solid cylinders. So that information is important. For the solid cylinder, if you go to your table of moment of inertia, for the solid cylinder is half mass of the cylinder and the radius squared. Okay, that you need to take from the if the question given that you can use it. If not, you need to go to the table and find out that. And axis pass through the center of the both ends of the cylinder. Cylinder A has the 3 times of mass of the cylinder B. Those information is important. Mass of cylinder A is equal to 3 times of the mass of cylinder B. Write down the given information. But they have same radius. Radius of the cylinder A is equal radius of the cylinder B. Okay, now we have enough information. In addition to that, it say they have same rotational kinetic energy. What we need to find it out is this ratio. Okay, so now kinetic energy, definitely rotational, of A cylinder is equal to kinetic energy of rotation of B cylinder. Now let's write it down as we know. I A cylinder omega A cylinder squared should be equal half I B cylinder omega B cylinder. Okay. So half cancel out, and then I'm going to take the ratio first. I need omega A over omega B. I'm going to divide by omega B squared in both sides. Right? When I do that, this will cancel out, and then I have omega A over omega B whole thing squared is equal, I'm going to divide by IA in the both side, IA, and you're going to write the new step on your side. Cancel out, and then I have IB over IA. Okay, so now let's rewrite this. IB over IA. How do I write it? That is half mass R square. I'm going to write it half mass of the A object, now B object, so B is the numerator, and R B object squared divided by half mass of the A object, R A object. Half cancel out. So now I'm going to write in terms of one of that. I'm going to write I'm going to write in terms of B, right? So MB I'm just going to keep as it is, MB RB squared. I'm going to divide by MAR squared. MA equal 3MB. Because of that, I'm going to write 3MB. And RA is equal to RB and RB squared. As soon as you do that, you see that this thing cancel out, this thing cancel out. Then you have 1 over 3 left. Okay, so now omega A over omega B is the one asking. Because of that, what I have right now, I'm going to rewrite my final formula, 1 over 3. Now what you're going to do, we're going to take the square root of this side, square root of this side. Then you're going to end up with omega A over omega B on the left equal 1 over 3 and root. That will be your final answer. Okay, so let's stop here.